welcome back to the Explainer. I am so glad you're here. Today, we're diving straight into some Go code, specifically a function called RevConcatAlternate. We're going to break it down, strip away all the noise, and really look at the anatomy of this algorithm in tangible, bite-sized parts. By the end of this, you won't just see lines of code, you'll have a crystal clear picture of exactly how this logic pieces together. Let's get into it. Here's our agenda for today. 1. Function overview. 2. Finding the starting point. 3. Priority, larger slice leads. 4. Tracing the execution. And 5. Handling edge cases.
Number 1. Function overview, the concept.
So conceptually, what are we doing here? Well, RevConcatAlternate takes two distinct integer slices and mashes them together into one single slice. But it does this with three very specific twists. First up, it concatenates them in reverse order, meaning it grabs elements from the back of the inputs first. Second, it alternates those elements. It takes one from the first slice, then one from the second, kind of like the teeth of a zipper locking together. And third, it prioritizes the longer slice, making sure that one takes the lead. Okay, take a look at the complete RevConcatAlternate code block right here in Go. If you spend a lot of time manipulating slices, you're probably looking at the variables in the loop and thinking, hey, this is essentially just a standard concat-alternate function. And you'd be absolutely right. But instead of iterating forward from index 0, this whole thing is specifically wired up to iterate completely backwards. Moving right along. 2. Finding the starting point, setting up the loop. To actually go backward, the algorithm first has to figure out the absolute highest index between the two slices. And it uses a really clean three-step logic to do this. Step 1. It just arbitrarily assumes the first slice, S1, is the longest, and sets a variable called max to the length of S1. Step 2, it simply asks, hey, is the length of the second slice, S2, greater than our current max? And step 3, if yes, it updates max to equal the length of S2. It's super straightforward, but it flawlessly sets up our ceiling. Right, so once we have that ceiling, the loop fires up. It starts at max minus 1 and counts all the way down to 0. Now you might be wondering, why minus 1? Well, slice indices are zero-based, of course. But here's the brilliant part. Starting at the absolute highest index and counting down guarantees that we process the extra elements of whichever slice is longer first. Because we're appending to a brand new result slice, those extra elements from the back of the longer slice end up right at the very front of our final output. Section 3. Priority larger slice leads. Now, what's really interesting here is the sharp contrast between the two main conditions. Inside the loop, the code checks if len of S1 is greater than or equal to len of S2. If that's true, slice 1 wins the priority tiebreaker. Its element gets appended first, and then slice 2 follows. But if we fall into that else block, which means slice 2 is strictly longer, the append order completely flips. Slice 2 appends its element first, and then slice 1. Looking at this priority logic in action highlights something absolutely crucial: the guard clauses. See those inner if I is less than len of S1 and if I is less than len of S2 statements? When our index I is hanging out in that extra range, meaning it's a high number that only the longer slice actually possesses, only one of those if statements is going to fire. The shorter slice fails the guard check, which totally saves us from a program crashing out of bounds error. The longer slice just contributes all on its own. It's only when I counts down far enough to fall within the bounds of both slices that both if statements start firing and the elements beautifully start alternating. On to number 4, tracing the execution, visualizing state changes. Let's trace this out with an equal length scenario. Imagine slice 1 is 1, 2, 3, and slice 2 is 4, 5, 6. Both have a length of 3. Since they're equal, our priority rule says slice 1 leads. Our max is 3, so our loop index I starts at 2. At I equals 2, we append slice 1's element at index 2, which is 3. Then slice 2's element at index 2, which is 6. So our result is 3, 6. Then we drop down. At I equals 1, we pull 2 and 5, giving us 3, 6, 2, 5. And finally, down at I equals 0, we pull 1 and 4. Our final result builds step by step to 3, 6, 2, 5, 1, 4. But what happens when the lengths are mismatched? Let's say slice 1 is 1, 2, 3, but slice 2 is 4, 5, 6, 7, 8, 9. Slice 2 has a length of 6, making it the undeniable leader. Our max is 6, so I starts at 5. For the first 3 loops, I equals 5, 4, and 3, slice 1's guard clauses fail. It literally has no data there. So slice 2 populates the first 3 slots entirely on its own with 9, 8, and 7. It's not until I equals 2 that slice 1 finally comes into range.
From that point down to 0, the slices alternate, 6 then 3, 5 then 2, and 4 then 1. And honestly, this brings up an incredibly interesting observation from our source material about this exact code block. As the quote here points out, because slice 2 started out longer, it gets locked in as the leader for the entire loop. Even when I drops down and both slices are technically equal in the remaining range, slice 2 still appends first, giving us a sequence of 6 then 3, 5 then 2, 4 then 1. The author notes that sometimes expected behavior might dictate that slice 1 should take back the lead once the sizes are effectively equal mid-loop. It is a fantastic reminder that tracing your execution is literally the only way to see if your code's strict logic actually matches your expected edge case behavior.
And finally, 5. Handling edge cases, pressure testing the logic. When we start throwing curveballs at this logic, it's pretty awesome to see how it handles them. We already saw that equal lengths are cleanly resolved by the greater than or equal to operator, locking slice 1 as the leader. But what if one slice is completely empty? Well, the algorithm doesn't panic. The loop still runs based on the populated slice's length, and the empty slice simply fails the guard checks every single time, safely doing absolutely nothing. We also saw how those extra elements are seamlessly processed all alone at the top of the loop. And if both slices are entirely empty, the max is determined to be 0. The loop condition I greater than or equal to 0 with a starting I of -1 means the loop never even fires, instantly returning an empty result. Talk about bulletproof. This algorithm is just a masterclass in defensive programming, which leaves us with a final thought to ponder. How does the incredibly simple I is len guard clause serve as the ultimate safety net for algorithmic slice manipulation? I mean, it's just a few characters, right? Yet it completely removes the need for complex, nested looping structures, allowing a single loop to gracefully and safely handle mismatching datasets. Think about how you might apply this kind of elegant pattern, establishing a maximum ceiling and using guard clauses in your own daily logic. Thanks so much for joining me to explore this algorithm today. Keep learning, keep tracing, and I'll catch you in the next explainer.